Welcome to the next week in our continuing series on what is sound. And we're going to begin with a review from last week of the decibel. If you remember, the decibel in simplest terms is just a ratio between two numbers. It's often used in sound recording or sound engineering as or in preference to other units, volts or watts, since it's a convenient way to express the ratio of one value to another. And the results are more convenient since many sound-related comparisons involve very large numbers, and using a logarithmic scale like the decibel allows those large differences to be expressed in smaller units. For example, the human hearing ranges from 0.0000000000001 watts per meter squared to approximately 100 watts per meter squared. And in decibels, that's only a range of about 140 decibels. So the decibel is based on a base 10 logarithm of the ratio of two numbers, and it describes how much larger or smaller one value is from another. And the equation is decibels equals 10 times the base 10 log of the two values, in this case P1 and P2, where the initial value is P1 and the second value is P2. For example, if P1 is 2 watts and P2 is 1 watt, then to go from 1 watt to 2 watts, putting the final value on the top, you end up with approximately 3 decibels. So an increase of 3 decibels results in doubling the power. An increase of 6 decibels is quadrupling or multiplying by 4 the power. And a decrease of 3 decibels is halving the power, or going to 1/2 of what it originally was. So looking at the example above, if we wanted to go from 1 watt to 2 watts, you see the equation there, and it's an increase of 3 decibels. If we go from 2 watts to 1 watt, it would be a decrease of 3 decibels. Now, we also brought up last week the difference between power and voltage, how they're calculated in decibels. And this week we're going to introduce or add current to that list. So if you remember, power was 10 times the log of P1 over P2. Voltage and current are both 20 times the log of V1 over V2, or I1 over I2, where I is the symbol for current. We also discussed that the decibel had sometimes was expressed with a reference. So dBV will always put 1 volt on the bottom of that fraction. dBu is the European standard, and that would put 0.775 volts on the bottom of the fraction. dBV is little v, is the 0.775 volt standard in the United States. dBm, the M standing for 1 milliwatt, and dBA, A references the weighting of the sound pressure level. And we'll talk about the sound pressure level weightings later in this lecture. So here's a quick cheat sheet. If you don't want to memorize or you don't want to have those equations with you all the time, simply remember that when you double, going, for example, from 1 to 2, you increase by 3 decibels if it's power, or 6 decibels if it's voltage and current. And to cut something in half, in this case going from 2 to 1, it's a decrease of 3 decibels for power and 6 for voltage and current. If we quadruple or multiply by 4, we basically multiply by 2, that goes up 3 decibels, and then 2 again is another 3. So 3 plus 3 is 6. And likewise, if we decrease by a factor of 4, we cut it in half, and then we cut it in half a second time, and that results in a decrease of 6 decibels. And of course, the voltage and the current numbers are always the power value just doubled, because we're multiplying from the equation by 20 instead of by 10. So by a factor of 8, we're looking at an increase of 9 decibels. 1 to 2 is 3, 2 to 4 is 3, and 4 to 8 is 3. So 3 plus 3 plus 3 is 9. And likewise, a decrease by a factor of 8 is to decrease by 9 decibels. The next one would be increasing by a factor of 16. And of course, that is simply going up to 12 decibels, either increase or decrease. Now notice I skipped one section in between because there's one other number that is of importance if you're just trying to remember the technique here without having to use the equations, and that is a factor of 10. So to increase by a factor of 10 is to increase by 10 decibels. And voltage and current obviously would have that doubled. So therefore, the two things to take away from this whole sheet is when you double, you go up by 3 decibels. When you go up by a factor of 10, you go up by 10 decibels. And from those two, you can pretty much figure any other decibel change out within reason. And then one more that I'll throw in there is an increase by a factor of 100 is 20 decibels. So we can see here how using the logarithmic decimal scale takes very large differences and makes them much smaller. A factor of 100 times is only 20 decibels. And if you remember, a factor of 10 was 10 decibels, and we got to 10 by multiplying by 10. So 1 to 10 was 10 decibels. If we multiply 10 by 10, so it's still just a multiple of 10, we get 20 decibels. So 10 plus 10 is 20. So again, the multiplication of the power and or voltage and current is turned into simply addition. So kind of spend a few minutes looking at this table and try to understand just a little bit of how the doubling works and then how the factor of 10 works. And if you have the doubling and the factor of 10 figured out, the rest of the stuff should be pretty simple as far as the decibels. The next section we're going to step onto is sound power and sound intensity. Simple sound sources radiate power equally in all directions. They are called omnidirectional. And if you think of a ripple from a stone dropped into a pond, it's very similar to that. And this was the very first slide we looked at in week 1, except it radiates in a sphere, not just two-dimensional like the ripple on the pond. And sound is measured in watts as the sound spreads in all directions from the source. The power per square foot decreases by a factor of 4 every time the distance doubles. So for practical purposes, the sound intensity level drops by 6 dB for every doubling in distance from the source. And if you remember, we dropped by 3 dB if the power decreased by a factor of 2. In this case, the second paragraph says the power per square foot decreases by a factor of 4 every time the distance doubles. And that's where the 6 decibels comes from, is the factor of 4 every time you double the distance. Do not confuse the power output of the amplifier, which is measured in watts, with the acoustical power of watts. Loudspeakers are very inefficient, converting only a small amount of their electrical input power to acoustical output power. In fact, most speakers, well, actually all speakers, are much, much better at being heaters than they are producing sound. So if you were to go into a large speaker system and touch the back of a speaker during a concert, the speakers would probably be extremely hot. Now, to go on and talk more about how sound and the sound intensity changes as we move from a sound source, we have to go back to Isaac Newton's research in what he came up with as the inverse square law. According to his research, we know that sound or travel of sound behaves similar to other waveforms. And Newton's inverse square law is based on a spherical, if you remember, spherical is the omnidirectional radiation of the sound. And although to a loudspeaker above about 100 hertz, the sound is mostly directional, just because of the way speakers work, the attenuation of the sound up to about 3,000 hertz projected over a distance has enough similarity to be calculated with this law. So simply stated, the inverse square law states that by doubling the distance, the sound pressure level will be halved, which is a reduction of 6 decibels. Now the power, remember, is 1/4, but the sound pressure level is 1/2. So this is now following the 20 log formula. So here's a table and a picture that kind of describes this. And if you remember, we're just looking at one small section of this sphere. And if we have a sound source that at 3 feet is 100 decibels, every time we double the distance, we drop by 6 decibels. So at 6 feet, we'd be at 94. 12 feet, we'd be at 88. 24 feet, 82. 48, 76. 96, 70. And 192, 64 decibels, dB sound pressure level, dBSPL. Now, one other thing to be mindful of here is I will be giving you the PowerPoint notes for each week, and I would recommend that you print the PowerPoint notes because you will be allowed to use them on the exams. It's one thing to memorize the concepts. It's another thing to have information such as the reference sheet or the cheat sheet a few slides back and this slide on the exam. Because there are things that you should memorize and there are things that you should be able to look up. So you will be able to use your notes. Now, to talk more about Newton's inverse square law, in order to increase the sound intensity level by a factor of 2 or 6 decibels, we need 4 times the energy from the source. Every time the distance has traveled has doubled, the projection surface has quadrupled. That's why it's a factor of 4. And just as a reference, 0 decibel sound intensity level is equal to 10 to the minus 12 watts per meter squared. That's that 0.0000000000001 watts per meter squared. That's the quietest sound that any human can hear, because basically there is no sound at that point. So, looking at the equation, if we want to go up by a factor of 4, we're going to multiply that 10 to the minus 12 by 4, and we get 6 dB SIL. So we've increased 0 decibels by a factor of 4, and we're at 6 decibels. The formula for sound pressure level says that 0 dB SPL, which is actually the quietest sound that we can hear, is about 20 micropascals. And therefore that converts to 6 dB SPL as well as the 6 dB SIL. Now these equations you will not need to know. They're just here for reference. And then the final thing we're going to talk about related to Newton's inverse square law is if you look at the orangish red lines on this chart, they are what the different sound in cycles per second at 1,000 feet register. But if you notice, the relative humidity goes up, therefore the sound level goes down very quickly with high frequencies. So the less humidity, the more high frequencies will travel through the air. And the black lines keep the relative humidity the same. So If you had a 3,000 hertz or 3 kilohertz sound at 80 decibels, when you get 1,000 feet away, it will have dropped to about 70 decibels just because of the relative humidity. A 6,000 hertz signal will drop by approximately 15 decibels from 80 to 65 at 1,000 feet. And a 10 kilohertz, which is the beginning of the top octave that humans can hear, will drop from 80 almost all the way down to 40 at 1,000 feet. And that is the difference in relative humidity. So this would be added to the sound pressure level change that would occur over that distance. So sound pressure or loudness is measured with a number of different standards, and you've heard about a few of these already. You've heard about the watts per meter squared at the bottom there, and you've heard about dBSPL and microbars and FONs, and the other one is Pascal, which is newtons per meter squared. Of all of these, we're going to focus only on dBSPL, and that again is the 20 log of the original power divided by the second power divided by the original power, and it's 1/4 as you move away from the sound source. So here are some typical sound pressure levels, just to kind of give you a bit of reference. So starting at the bottom, 0 is the threshold of hearing. 10 is the distant sound of rustling leaves. 20 decibels dBSPL, is the background noise in a TV studio, relatively quiet. 30 would be a quiet bedroom at night. 40 is a quiet library. 50 is about the average home. 60 is two people having a regular conversation at 1 meter distance. And 70 would be a vacuum cleaner about a meter away from you. 5 meters from the curb, listening to a busy road, is about 80. A diesel truck at 10 meters is 90. A lawnmower at 1 meter would be about 100. And 110 is a chainsaw at 1 meter. And then at 120, our ears actually start to hurt because we're at the point of distance that most typical eardrums can travel. Above 120, you could have physical damage to the eardrum, and if the pressure is high enough, it could cause immediate death, not from the sound itself, but from the pressure of the sound. So here is a diagram of pretty much how our ears work. Our ears have an ear canal, and at the end of the canal is the eardrum. The eardrum receives the direct pressure of the sound and indirect pressure through the nose and the eustachian tube in our throat. And that's sort of how we hear ourselves, and why when you plug your nose or plug your ears and talk, you sound kind of nasally or kind of weird. Our ears, the way they work, is very similar to a cardioid mic pattern, and we haven't really talked about cardioid yet, but each ear tends to reject more of the sound coming from the other side of our head, obviously because our head's in the way. And our ears, together with our brain, are capable of simultaneously locating, analyzing, and separating multiple sound sources. But this is highly sophisticated, and it's limited, and our sensory system can be fooled or overstimulated as well as overloaded. And we experienced a little bit of this in the Laurel and Yanni experiment or audio that you listened to this past week. The limitations defined by the threshold of our sensory capabilities is the perception thresholds. And here are a couple of those threshold levels. Levels over 140 dBSPL can cause immediate hearing damage, and that's permanent hearing damage, and sometimes have been proven deadly. Levels greater than 120, which is the threshold of pain, can permanently damage our hearing. And levels greater than 100 lower the perception of our brain to determine the exact frequency of musical intervals by about 10% in either direction. And this can be demonstrated if you've ever been in a loud club or a loud concert and the singer sounds fine, but you have to step outside to take a phone call, use the restroom, etc. Often once you step outside, you realize that the singer really isn't singing in tune. And that's because the louder the sound, the more the less accuracy we have when we try to repeat or duplicate a sound. And this will come in handy in the recording studio as well. You want to make sure that the headphone monitor levels aren't too loud for vocalists or other musicians, because that will affect how they sing or how they play their instruments. Now, from here, we just talked about perception thresholds related to the level of sound. We're going to move to the concept of time. When two events happen within an interval of less than 10 milliseconds, we are not capable of determining whether the events happened separately or simultaneously, but we will perceive them as happening at the same time. The tenth of a second or 10 milliseconds is an internationally accepted standard and is used in calibration of audio program level meters, and was also the basis for the MIDI specification. If you know, MIDI is the Musical Instrument Digital Interface specification, and it's the cable that plugs from multiple MIDI instruments into a computer. And they decided that if the MIDI signals, which are sent out sequentially one after the other for all the different simultaneous sounds, if they could all occur within a tenth of a second, to the human hearing, it'll sound like all of those events happened at the same time. In contrast, our eyes have a much slower threshold, and movies at 24 frames per second are perceived as fluid motion. The next hearing perception threshold that we're going to look at is that of frequency. And by virtue of the upper limit frequency spectrum for human hearing, generally the range being from 20 to 20 kilohertz, any waveform with a fundamental frequency of greater than about 8,000 hertz will almost always be perceived as a sine wave, because the second harmonic of the 8 kilohertz fundamental is 16,000 hertz, and the second harmonic of a 10 kilohertz signal is at the upper limit of most human hearing. So the upper limit's being 20K. In reality, it's much lower than that, because as we get older, our upper end hearing usually diminishes. So again, everything from about 8,000 hertz up will almost always sound like a sine wave to us, regardless of the frequency content. So now, looking at frequency, men and women hear differently. And research has found that women have hearing that is sometimes up to 3 times more sensitive than men. And this equates to approximately 10 decibels. The difference between men and women found that in women, they preferred a nominal listening level of about 75 to 85 dBSPL as comfortable, while men preferred 85 to 95 dBSPL. So what we're going to find out later on in today's lecture is that we've determined a nominal listening level for recording studios. And we'll talk more about that in a few slides. As well as women's hearing being more sensitive sound-wise, it's also more or better capable of hearing high frequencies. Most young people can hear up to about 18 kilohertz, some more, some less, and our ability to hear frequencies declines with age. So by age 55, some men can't hear above about 5,000 hertz, and some women can't hear above about 12,000 hertz. Now, we've also talked a little bit about the dB/SPL with the A weighting. Basically, our ears can detect a limited range of frequencies from the 20 to 20,000 hertz range. And within this range, our hearing is far from linear. We are far less sensitive to the lower and the higher frequencies than we are to the mid-range frequencies, say from about 150 hertz to 5,000 hertz. And most vocal communications occurs in the mid-range frequency band, with our ears being most sensitive right around 4 kilohertz. And this corresponds to the resonant frequency of the ear canal. So aside from the general less sensitivity to lower and higher frequencies, our hearing sensitivity is also dependent on the sound pressure levels. So the louder a sound is, the least sensitive or less sensitive we are to differences in the levels of the frequencies. And initially, two scientists, Fletcher and Munson, in 1933, came up with what we knew as the Fletcher-Munson curves. And in 1956, they were updated by two scientists, Robinson and Dadson, and they are now officially called the equal loudness contour curves. And this is what that chart looks like. So if you look at the horizontal lines, they represent sound pressure level corrected to the perception of our ears, hearing them as constant loudness. And again, you won't really have to memorize this, but just understand that right around that 1,000 to 10,000 range, our ears are more sensitive to the sound than they are at the upper end or the lower end, where they needed to turn the sound up louder in order for it to be perceived as the same level. And if you've ever seen a loudness button on a stereo system or in your car, the loudness installs a filter into the signal flow that mimics these curves in reverse. So they basically are increasing the low frequencies and the high frequencies to make them sound better at lower listening levels. So they would basically be looking at the lower, the 0, 20, or 40 curves and trying to flatten them out closer to the 100 curve by applying filtering to your sound. Now, the equipment for measuring frequency response or noise or signal to noise levels in an environmental situation are either environmental noise meters or real-time audio analyzers, also called RTAs, and they use electronic or mathematical filters in order to allow the equipment to measure electrical or acoustic noise levels. And the frequency response is therefore adapted to match not what the microphone hears flat, but what we hear with our ears. And when we talked earlier about the dB/SPL with the A weighting, you can see the A weighting curve there. So basically, we are going to adjust the way these frequency analyzers and sound level meters react to match human hearing. So you'll often see the levels in dB/SPL-A, which is applying this filter to the measurement so it mimics human hearing instead of the Z weighting or zero weighting, which is the actual sound the instrument is picking up. Now, the A and the C weighting are used for signal to noise specifications of audio equipment. They're also used in an environmental setting to look at noise levels in factories, highways, or airports, and it's what's used to investigate nuisance complaints from neighbors for too much sound. The exhaust noise of motor vehicles is regulated, and it will also use either the A or the C weighting the interior noise levels from air conditioners and appliances. Interesting note here, air conditioning in office settings is intentionally noisy to put a level of separation between people's conversations in the office. You can also measure transmission loss through walls and doors and windows. And the nominal studio monitor level is weighted at 85 dBL or dBSPL, a weighting for a nominal level. The A weighting curve covers the full audio spectrum range, roughly the frequency of sensitivity of human hearing, and it follows the 40 Fon equal loudness contour from the equal loudness contour chart we saw before, and it's usually shown as dBA or dBSPLA. And the C weighting is roughly the way our ears hear at right around 90 dBSPL, and that will be abbreviated as dBC or dBSPLC. So here are the roll-off frequencies for the different weightings, with Z being flat response, and then the C dropping by 0.8 decibels at the low level and 8.5 at the very high, and then the A weighting having the largest drop-off at the lower frequencies. Again, these are just for reference. There won't be questions about these on the exam, or if they are, they will be very, very, very basic questions. So now we get back to the comment earlier where men and women had slightly different hearing preferences in terms of the loudness. Women preferred 75 to 85 and men preferred 85 to 95. So the internationally accepted listening level in a recording studio is 85 decibels at the ears of the listener. And this is also where the equal loudness contour happens to be the flattest, and it seems to be a point that both male and female listening appear to sound comfortable. And anything higher than about 85 or 90 decibels will have lasting hearing damage that is either permanent or residual, meaning that if you are taken away from the louder sounds, after a while your ears will return to normal. So here is basically how you would calibrate a sound system. You'd have a noise generator that generates pink noise into the system at a master level of 0 dB VU or 0 dB with the VU standard. You'd place a sound level meter set for A weighting in the listening area, and that would be where the guy's head is at the bottom of the slide there. And then you would adjust the power amplifier so the 0 dB on the recording console is registered at 85 dB SPL at A weighting at the listener's ears. And this is the end of this video. And again, I will post the PowerPoint slides. I encourage you to print the slides from all of the weeks and have those as reference as you go through the quizzes and when you go through the exams.